So welcome everybody to this meeting of the IEEE Pittsburgh Section Robotics Society. We're honored to have Spencer Krause speaking this evening and Chuck Whitaker as well to introduce him.
Thank you, Al. Okay. So welcome to Carnegie Mellon. Spencer's been, he was a master's student here about 8 years ago. And I worked with him while he was doing that work here at Carnegie Mellon. Saw him play around with his battle bots, and he joined us with Girls of Steel, and then carried on and did his master's work. And he's now the CEO of SKA Custom Robotics, and he's going to talk to you about field operations and robots and how they succeed and don't succeed.
Thanks, Chuck.
And a lot of times they don't.
Plenty of times they don't. Thank you so much. Yeah, so what Chuck said couldn't be more true. I remember a time I crashed a robot through a wall here on campus as an undergrad. And that sort of thing happens more often than you would think. So the original theme for this talk was Robots Gone Wild. And I was going to tell a bunch of stories like that and just try to sort of humanize failure in robotics, because as Chuck said, it is more common than not. But I think as engineers and company people, we kind of hide that sometimes. That said, I thought about it some more, and I thought, well, this is IEEE, this is prestigious. I want to give a talk that's tonally appropriate and educational for people. Hopefully it doesn't put you to sleep. And I've rolled some of Robots Gone Wild into it. It's called Advanced Development Tactics for Field Robotics. Thanks for coming, everyone. All right, so I've worked on a lot of things over the years. I've been building robots for 22 years now. And a lot of what I've done as a robotics professional has been confidential, which means I can't really talk about it in front of an audience. And so in order to get around that, I'm going to be talking a lot about a robot that my company SKA worked on as an internal research and development project called Rucktro. As you can see, Rucktro is a following robot that's designed to move medium around a landscaping site. We pursued it for a while and then just decided that it probably wouldn't be commercially viable, and we pulled the plug on it. So as a result, I'm free to talk about it, and I can show you kind of some of the nuts and bolts that went into building this thing. All right, so bottom line up front, this is what I'm going to be talking about today. These are the techniques. So one is systems engineering. When I was a kid, I would go about building a robot in that I would buy a bunch of parts I thought were interesting from McMaster-Carr and Robot Store and DigiKey, wherever. I would just kind of get the stuff off the catalog, and I would wind up with a pile of parts, and I would try to make them all fit together, and oftentimes they wouldn't. And so then I'd buy more parts with money I didn't have from my parents that I begged for, and then I'd kind of repeat that 3 times, and I'd end up with a robot that sort of worked at the end. So the systems engineering is a discipline that the MRSDs here understand pretty well and appreciate, where you define how all the bits of a robot come together to make a whole that's greater than the sum of its parts. So my iPhone is awesome. It wouldn't really be awesome as a pile of ICs and silicon. That's kind of the point of systems engineering. So the next thing I'm going to talk about is testing subsystems. So when I say testing subsystems, what I mean is starting from parts in terms of testing, validating that those work on the bench, and then working your way up to a complete robot. So you get a motor, you test that, usually in Vice. You build up your system, you test different features, current limit maybe. You then integrate that into your drivetrain or your mechanism. You test it there, you make sure it doesn't have any hiccups, and you continue to build up. Low-cost test platforms, aka test mules, or what I call them in this talk. This is an inexpensive version of a robot that is made from inexpensive components so that you can parallelize the development efforts. So a lot of times, I've worked on multi-ton mining vehicles and construction vehicles and different robotic systems that are very expensive individually. But if you build a surrogate, you can test your autonomy system. And I'll show you one that we built for Rucktro, where we actually mailed them in Pelican cases to different autonomy engineers that are working remote. And then finally, simulation. Personally, I don't use this one as much, so I'm kind of just going to gloss over it. But obviously, you can test software on hardware that doesn't exist yet. It's a great tool to have in your belt, and so we'll go over it briefly. And obviously, testing this stuff increases the probability of success in initial hardware tests. I'll go into some examples of why that is when I get into the talk there. All right, so systems engineering. First of all, shout out to the NASA Systems Engineering Handbook. If you don't have this, you should get it. It's free, your tax dollars pay for it, and it's awesome. So it's a few hundred pages, and it's just got an appendix full of templates for, basically all these different things: concept of operations, physical architecture, states and modes, state machine diagrams, requirements, D&D plans, and a bunch more stuff I'm not going to talk about because it would, just be too long of a talk. You guys will get that from Dimmy later. So anyway, again, the reason to have systems engineering is to define how a bunch of parts go together to make a sum of the parts that is greater than the parts individually. Concept of operations is a usually text document with some pictures in it that describes why a robot wants to exist, the market need, and how it functions, sort of in the abstract, and then how people interact with it. The physical architecture is a block diagram. I've also heard it called a systems block diagram of components. So one example of component might be a motor, drive, low-level ECU, and then like high-level compute module. And you typically show how those are connected in terms of power and data, and then sometimes torque and fuel and pneumatics and hydraulics and things like that. So it's a way to conceptualize the system early on that you can kind of get all the teams behind and start to part it out and do lower level engineering, mechanical, electrical, firmware, what have you. States and modes or state machine diagram. So the states and modes are the different states a robot has to exist in order to function. A lot of times these are exist in software. I'll give an example of something a little different here shortly. And the state machine diagram shows from start to end kind of the transition between those different states and modes. Often on the edges, you'll have a condition that causes a state change, and then sometimes you'll have like a loop back if something persists in a state under a certain condition. So requirements are sort of, the way I'm going to describe it, just this is the Cliff's Notes version, is it's sort of twofold. So you've got your engineering requirements, which can be verified against. So, like end of robot must be within 1.5 centimeters of target in outdoor full light conditions. Something like that would be an engineering requirement. But on the other hand, you've got your user requirements, like robot must not be physically intimidating to people, or like, must be pleasant to interact with, or, must have large enough font for an adult male between the ages of 50 and 70 to be able to operate, Something like that, where the way that you make sure that you did those things is by validating the complete system in user trials. So pretty different, and that kind of brings us nicely into verification and validation of D&D plan. That's how you test it, or at least the first unit before it's a little different than QA. It's how you test it and you make sure it does all the stuff it's supposed to do. So verification, as I stated, is how you verify that all the engineering requirements are met. You either do that through math or simulation or testing, or some combination of all the above. And then validation is where you run either like a model test mule of the complete system or the complete system to ensure that it performs its function in a way that's satisfactory, and then work on it, make it better. So some examples of systems that we've done systems engineering on are a retail inventory monitoring robot, a multi-robot construction system, and a ruggedized sensor system for mining and construction vehicles. All right, so I'm going to go through kind of a relatable example. So for anyone that's ever eaten a hamburger, which I'm guessing is probably all of you, this might look very familiar. But imagine you've never had a hamburger before and somebody just hands you this pile of stuff and says, make food with it. Well, you might end up with something that looks like this. Not good. So how do you get around that? Well, we're going to systems engineer a hamburger. So let's start with the concept of operations. For centuries, humankind has enjoyed bread, meat, and condiments from the comfort of a table or flat rock. With today's modern culture of hustle and bustle, there exists demand for meat and bread that can be consumed on the go. The hamburger is a portable amalgamation of the aforementioned ingredients designed to please both the senses and satisfy hunger while on the move. So obviously this is a very abridged concept for a hamburger. You don't want to spend that much time on it. But you can see sort of the first sentence establishes the status quo. Second sentence establishes a need, why does it exist? And the final sentence talks about what it is and how you interact with it. It should smell good and taste good and be able to be consumed while moving. Physical architecture, right? So in solid lines, we have our mandatory system components, the upper bun, the patty, the lower bun. And then with the dotted line, you've got your optional lettuce and cheese. So if you connect those things in that direction, in theory, you'll end up with a valid hamburger. But wait, there's more. So we've got requirements. It's got to be able to stand up on its own on a plate. It's got to be able to support the quasi-static load when you handle it and not break in your hands. It's got to utilize 6 to 8 ounces of beef or beef substitute. This last example did not. It's got to smell good. You don't really have the ability to quantify that, so that's got to come out in validation. Also, the bun must be fresh and free of mold, and the grease from the patty shall not permeate the lower bun. We've all had a burger like that, it sucks. Nobody wants that burger. All right, so to draw this example out even more, I'm going to go through a state machine diagram for a hamburger. So we're going to start here with a freshly prepared burger. Now, the obvious route here is consumption, and that brings you to the end state. But alternatively, you can wait 1 to 2 hours until the burger is spoiled and then throw it away. So those are the states and modes of a hamburger. All right, so if you follow all these things, you should end up with a real hamburger and not that monstrosity I showed earlier. Now, to give a better example for robotics, this is a subsystem for a retail inventory tracking robot. So the top box is a safety supervisor node. That connects via Ethernet to a switch in the middle. You can see power is brought in from the left. Usually left to right is a good flow for power and data. There's a bunch of Ethernet going out on the right for stuff, which I'm not going to get into because the font's really small. But then coming off the safety supervisor node, you can see encoders, analog sensors, e-stops, an inclinometer, and a bunch of current sensing. Off the switch, you've got some 3D cameras, a LiDAR, and then you've got this, what's called the embedded master node at the bottom. And what that does is it connects via Ethernet to the switch, and then breaks it out into CAN bus to talk to a bunch of other stuff that's not pictured in this particular slide. So yeah, that's what it looks like in real life. All right, so going on to building and testing subsystems. As stated, you want to do this so you don't end up integrating components that aren't viable. You can also break out work into a greater amount of teams. So if you break out different robot subsystems, you can assign that work to different groups of people and accomplish more in parallel. A bunch of reasons to do this. How do you do it? So you break the problem down into discrete chunks, i.e. components or subsystems. You test the chunks and then integrate them into bigger subsystems, and then finally you put all that stuff on the complete robot. Sometimes you put some subsystems on a test mule, and others wait for the whole robot, depending on what you're doing. So some examples. So the driver module for hardware and a handheld navigational device is something we worked on. We worked on a surgical robot's collision detection and avoidance system as a discrete subsystem. And then pictured here is the track module for Rucktro before being integrated into the frame, which was tested on the bench initially. So to go with the Rucktro example a little bit more, you can see now the track modules with this frame welded around them are just 1-inch tube steel with a 16-inch wall. And then you can see it being programmed on the rightmost image over there. So those are the steps approximately. All right, so going into low-cost test mules. So as stated before, this is building a surrogate for your full robotic system, and basically entails, you find like a toy, or sometimes they make development platforms, ClearPath Robotics, SuperDroid, there's a few other companies that make them. I think Kinetic Talons are on auction right now, so that might be a good candidate for a test mule platform. I think you can get them for under 10 grand. At the moment, they used to be 400. But there's a bunch of ways to go about it. Some people use a wheelchair with just the motors and wheels, and we'll build off of that to test. Anyway, what you can do is mimic your sensor geometry on this platform, approximate your controls as closely as you can get. So if you've got a hydraulic drivetrain and you've got, in the full-scale vehicle, but you've got electric in your test mule because it's cheaper and you don't want to put a hydraulic pump to a test platform, I mean, that's fine. Just, you're going to have a little bit of time spent in integration, making up for that gap in controls as well. So, yeah. And then eventually, once you test everything on the mule and work out some of the kinks in edge cases, you can deploy your autonomy system to a full-scale vehicle. So I've worked on this on 12-scale miniatures of multiple mining vehicles, namely a robotic mining shovel and a robotic blast hole driller. So we built the miniatures in the lab first, tested on those, LiDAR, radar, GPS in the parking lot with RTK correction, a bunch of different sensing modalities and autonomies, self-collision avoidance, waypoint nav, etc. And then there's a variant of Rucktro that was done on this. And then the one that you don't think about very much is Chuck had mentioned BattleBots. So a lot of people, you see them on the TV show, and they've got this 250-pound behemoth. And something that a team captain that tried to call me recently for a team sponsorship was telling me, and it's very true, is that every team captain in BattleBots carries a $10,000 credit card debt. I'm not lying, it's the truth. So anyway, one of the ways that teams get around making BattleBots that don't really make sense or aren't competitive is they'll compete in lighter weight competition. So I always competed like 15 or 30 pound. I was never that good at it. I obsessed over building the thing and spent all my time in engineering and then never became a good driver. That's beside the point. So what you'll see is these guys that are on the TV show with like proofs of concept that'll show up, and maybe they'll do it. They have a 1.5 pound, a 3 pound, a 15 pound, a 30 pound, and I think some places in California still do 60 and 120 pound weight class. So they'll test it out, the smallest one first. They'll say like you want to build something with a saw that swings overhead. No one's ever done that before. You don't know if it's going to fight good. So you build it up and you see how it does. And if you win the competition, you might build it in a higher weight class or obtain sponsorship to build it at the 250-pound scale and take it on the TV show. So kind of a fun example there. So this is the test mule we use for Rucktro. You can see on the left the general platform. It's based off a toy chassis. That's fine. It's supposed to be. This was less than a third the price of building the actual vehicle. And you can see on the right side the payload that was fitted to it, because we tested a few things with this platform. This is the payload for Rucktro. So it's a horrible picture, I apologize, but basically what we've got inside is an NVIDIA compute module, that one's an NX, a Robotic controller for the motors. That's the same one the full-scale vehicle uses, even though it's silly on a robot this size. Just wanted to mimic the controls of the full vehicle as much as possible. What you can't see off the sides are two GPS antennae, and there's 7 real senses mounted on this altogether. Now, we found out with the test mule, 7 real senses is way too many for an NX. Wouldn't have known that if we hadn't tested it somewhere. So this was helpful. All right, some more close-ups just to kind of give you an idea of what's on the inside. You can see a bi-core power supply, a bunch of USB hubs, and kind of a, let's be honest, janky proto board with a 5-volt DC rail on it. The full-scale robot had a very, very nice PCB that was custom made for it with a bunch of 5-volt breakouts on it, but the input voltage lower band on that power supply and converter was lower than the maximum battery output on the test mule, so we couldn't use it. So proto board was designed as a quick and dirty surrogate. There's a DC to DC converter that provides the 5 that's tucked into the side that you can't see there. And that's how you built it quick and dirty in order to test, or how we built it quick and dirty in order to test. All right, finally, simulation. Why would you do this? Well, obviously no cost of hardware development. It can be used to test on hardware that doesn't exist yet, or rather software for hardware that doesn't exist yet. It increases your probability of success on initial hardware tests. When we've done simulation, we've found all kinds of things wrong with some initial geometric assumptions, and flush that out pretty quickly when you can visualize it. And it drastically reduces time to deployment because you can work on the software while the hardware is in development. How do you do that? So first you want to understand the important model characteristics of your full-scale platform. Then you want to build a minimally viable simulator, or ideally use a framework that already exists. VREP is one that was around when I was in grad school that I think has since changed into something else, Gazebo as well. And then there's a few paid ones. I think Duality is partially based out of Pittsburgh and has their own version based off Unreal. And then finally you want to move past it and build an actual machine. So an example of the way SKA used that is testing and demonstrating software module for a surgical robot that didn't exist yet. All right, so this is just a screen grab from Gazebo's webpage, so you guys get the idea. Same one for Copelia Sim, which is what VREP became, I think. And then a recap. So in summary, we've covered systems engineering at a very high level. Buy the NASA Systems Engineering Handbook for free. You can buy it on Amazon too. I have a paper copy as well. It's great. Test individual subsystems before building the full robot. Building a low-cost surrogate or test mule, and simulation. All right, if you've enjoyed listening to me talk this much and you're not clamoring to run out of here and get away from me, you might want to consider checking out my podcast. So what I do is I get really interesting people on, a lot of them local to Pittsburgh, that are running robotics companies, or I had the chief technical officer from Motive Space Systems on, a company that builds space robots, and we talked for like multiple hours on end. Get some really, really good talks there. If you guys want to subscribe on YouTube, the QR code will take you there. So please check it out. Like and subscribe. Interviewed Parag Batavia and Jürgen Pedersen, who will be teaching to the MRSD program. John Dolan's been on it. Try to get Chuck on as soon as I can twist his arm. But that's all I'll say about that. All right, so that's the talk. Thanks for coming.